one last video. I'm going to try to do this as succinctly as possible. So I want to find critical points, but in a function that has a domain restriction, and we're going to point out why that's important. So you're going to do this problem just like normal, just like every other problem. So we're going to take the derivative, and this would be low times the derivative of the high minus the high times the derivative of the low all over the square of what's below. And I'm just going to get rid of that one. Just there we go. All right, now set this equal to 0, and let's start solving. I'm going to distribute and work through in a couple steps. So here we go. So set equal to 0. And x squared, x plus 2 cosine squared, which should be x squared plus 4x plus 4, all that times 2x. Let's see, x, I'll leave the times 2, I'll do that at the end. X squared times x is x cubed plus 2x squared minus x minus 2. There we go. All over x plus 2 to the fourth. Now, when solving for 0, you'll notice this denominator, if we just multiply both sides by this, it's going to, this side would, x plus 2 quantity fourth. This side would just divide, right? So that would divide. And on this side, x plus 2 to the fourth, it's times 0. Anything times 0 always makes 0. So there's a little shortcut that we kind of keep in mind, is that when we're trying to take these quotient rules and we're trying to find out what makes equal to 0, you just really worry about the numerator. So anyway, kind of makes it a little simpler. So now for the numerator, we're going to keep distributing here. This 2x will distribute through, so that'll give us what? 2x cubed plus 8x plus 8x squared plus 8x minus 2x cubed minus 4x squared plus 2x plus 4. And combining like terms will result in those subtract, the x cubed subtract to make 0. So 8x squared minus 4x squared makes 4x squared. 8x plus 2x makes 10x plus 4. All right, solving. Let's factor whatever we can. So I'll take out a 2 to begin. So that gives us 2x squared plus 5x plus 2. And I'm going to go guess and check on this factoring. So I'm going to guess it's got to look something like this. It has to be plus or plus because it's positive 2. So whatever this number is here and here, they both have to make a positive, and they have to add together to make a positive. So therefore, they got to be positives. I'll put a 2 here and a 1 here, and I will check. 2x times 2 makes 4x. 1x times x makes 1. So 4 plus 1 makes 5. That's what we're looking for. So there's your correct factoring. Fantastic. All right. So now let's go ahead and set each term equal to 0. Each factor equal to 0. And I'm obviously skipping the 2 because 2 can't equal 0. So this is going to give us what? X equals negative 1/2 and x equals negative 2. Don't forget to always go back and check your answers. If I take x equals negative 2 and substitute that back in to the original problem, that would give me what? Negative 2 plus 2 squared with stuff in the numerator, which gives me stuff in the numerator over 0. That's undefined. So therefore, this cannot be an answer, but it is a domain restriction. And it is still going to go into our first derivative number line. So when I make my first derivative number line, I'm still going to have negative 2, and I'm still going to put negative 1/2. So now I want to point out, sometimes your domain restrictions come out in your algebra, like just happened. Sometimes they don't. So you always need to go back to the original problem and ask yourself, are there any domain restrictions that I need to put into my number line? And in this case, the only domain restrictions that come from a fraction is dividing by 0. So x plus 2 squared cannot equal 0. So when I do the square root, that just gives me x plus 2 can't equal 0, which therefore would be x cannot equal negative 2, which we already know. We already found that. Okay. Moving along. The next thing I like to notate is if it's a 0, I always put a point on it. This x equals negative 1/2 came from finding a 0. The negative 2 came from a vertical asymptote. If you need, go back and review the chapter 2, the early 2.1, the limits, to kind of talk about vertical asymptotes versus holes, which is how we determined big little logic and whatever. But anyway, so for now, this is a vertical asymptote. And it cannot be a max or a min. It's a vertical asymptote. Our graph is not defined there, but it is going to be important. So just like any other number line, we are going to test our 3 different regions that we have broken up here, the yellow, the blue, and the green. We need to pick a number to plug into our derivative, substitute our derivative, somewhere to the left of -2, somewhere between -2 and -1/2, and somewhere bigger than -1/2. I'm going to just show you in the calculator, just in case, just as one more opportunity to review. You can see I already have the function typed into my y1, the original function. For my y2, I'm going to just very quickly review. I'm going to type in the derivative, so I'm going to press math. Option number 8 is n derivative. New operating system, I'm going to fill in ddx. So I'm going to type in x. I want the variable of my the derivative of my y1 line. So I'm going to go to my vars button. I'm going to arrow over to yvars. It's a function, and I typed in y1. And then finally, I'm going to type in x. Old operating system people, whoops, I'm going to go to mode. You guys don't need to do this. This would just be for someone, just so I can show somebody what their calculator might be showing. Old operating system, you'll see when you hit that nderiv button, you got nderiv. You just need to literally be typing in the same way we did before. We're going to press vars, go over to yvars, hit enter for function for y1. Now that symbol there is a comma. You're going to put a comma. So comma, and then it's asking what variable is in the function written up above. So we're going to say we use the variable x, then you're going to do a comma, and now it's saying what value do you want? Well, and since I want 3 different values, I want something in my yellow region, something in my blue, something in my green, I'm just going to type in x so I can type in lots of different values. Okay, next. Table set. We're going to make sure our table is set to ask. Mine currently is, but if yours isn't, just arrow down, go over to ask, hit enter, and then you'll be set. Last but not least, we're going to go to our table. So we're going to press second graph, which gets us to the table. If you have values, just hit delete until they're all gone. And now we're going to type in values. I need some value to the left of -2. What would be to the left of -2? How about -3? There we go. Okay. And you can see our derivative was in the y2 line, and that is a positive value. Something in between -2 and -1/2. How about -1? You can see our y2 line that's a negative value. And last but not least, something bigger than -1/2. You can type in anything you want. How about 0? You can see that is a positive value. Fantastic. So now you can see there is a derivative, a positive derivative to a negative derivative. We have a derivative change. Does that mean we have a max at -2 because we went from increasing to decreasing? No, 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 no. We had a vertical asymptote there. So what our graph actually looked like at -2 is a vertical asymptote, and it looked like this. We went from a positive slope to a negative slope, but it's not a max or a min, right? So, okay, so enough of that. But we do have a decreasing to an increasing at -1/2. So therefore, I do have a critical value at -1/2. You can take that, sub it back into the original equation, and you will get a -1/3. Just one more little calculator trick, just to show you guys. We have the function typed in already, right? So I'm going to go vars. Oh, notice I'm doing this from the main cursor screen, main blinky screen. I'm going to press vars, yvars, hit enter. And then I'm going to use function notation. So I'm going to just do a parenthesis, -1/2, because that, whoops, -1/2, because that's the value we want to test. When I hit enter, it's going to say -0.333333, whatever. And if you want to see it in fraction form, because we're in the main cursor screen, I can just do arrow frac, and I can see that it actually is in fact -1/3. And I know it is a minimum from my number line that I have over here. So we just found that this graph has a minimum. And we can see how important it is that we know about this vertical asymptote. Because if you didn't know about it, if you didn't do the domain restriction and you only had the things that made it equal to 0, when you picked a number to the left of -1/2, it would be quite possible that you maybe picked -3 like we did, and you'd see it's a positive slope. You then pick something to the right and it would look positive, and it would look like you don't have any mins or maxes. So we need to know about those concavity changes, or not concavity, excuse me. We need to know about the derivative, the possible change in derivatives, sign of derivative, because of domains and restrictions. So that's why I wanted to show you this problem. I hope it made sense.